In this video, I'm going to introduce you to the moment of inertia. Now, the moment of inertia is basically how hard it is to get something rotating or change its rotation rate. It's kind of like how mass is how hard it is to get something moving or to change its velocity. So moment of inertia is to rotation what mass is to linear motion. All right? We generally use the letter capital I to represent moment of inertia. Before we dive into the mathematics, let's use some intuition that you may have. Imagine you're holding a set of barbells and you start to wiggle it back and forth like this. Compare how much effort it takes to wiggle the barbell like this. Let's compare it to what happens if we wiggle it around the axis of the bar like this. You see, it's just wiggling back and forth. Hopefully you have some intuition, some experience with playing with physical things that tells you that this type of motion takes less effort than swinging it up and down. In other words, rotating along this axis, where the yellow line is the angular velocity, right, we talked about in the last video, if we wiggle around this axis, it takes more effort than if we wiggle around this axis. Once again, the yellow arrow represents the angular velocity, which is a vector. Anyway, by looking at these two examples, we realize then that the moment of inertia depends on the direction of the axis. So unlike mass, where it's just some property of the system, right? This has, a mass m. When we talk about angular rotation, the moment of inertia of a given object depends on how we rotate it. It depends on the direction of the axis that we're rotating it around. Now let's look at this. Imagine you take off half of the weights and you grab one end of the barbell and start swinging it up and down. How much effort does it take to do this compared to swinging it about the opposite side like this? Probably your intuition is telling you that this would be easier to do than swinging it about the other end, right? Swinging on the side with the weights is harder than swinging about an axis on the opposite side from the weights. So in other words, swinging about this axis is more effort than swinging about this axis. So we've learned from that then that the location of the axis matters, not just the direction. In the last two examples, the axis was in the same direction both times, but it was displaced. So the location of the axis that we're rotating around affects the moment of inertia. So the moment of inertia of an object depends on the direction of the axis and the location of the axis. Now consider this. Let's compare wiggling our barbell like this to what happens if we slide all of the weights to the middle and swing it. So now we're swinging about the same axis, and we have the same mass, but we've moved the distribution of the mass. You probably have some intuition that says this is easier than swinging it with the mass on the ends. So from this, we realize that the moment of inertia depends on the distribution of the mass relative to the axis. All right, let's consider one more scenario. Let's compare wiggling like this to wiggling along the same axis, but we slid the weights along the axis. Now, you probably realize that it's just as hard to swing the masses, to swing the barbells, whether they're here or whether they're closer, right? And so from this, we realize that the moment of inertia depends only on the distribution of mass in the directions perpendicular to the axis. So if I move the masses perpendicular to the masses, or to the axis of rotation, it will change the moment of inertia. But if I move the masses along the axis of rotation, it won't change the moment of inertia. So let's see if our intuition holds. So here I have two structures. They're made of very lightweight bars, so we can ignore the bars, and then 8 masses at the corners. Which of these two structures has the greater moment of inertia about the axis indicated, the axis going right through the center of the structure? Well, in both structures, the balls all have the same perpendicular distance from the axis. The fact that some of the balls have moved along the direction of the axis, that we've squished them together on the right, will not change the moment of inertia because the distance of each ball from the axis is the same. So these two configurations have the same moment of inertia about the indicated axis. In this case, we've squished in the other direction, all right? So on the right, each of the balls is closer to the axis than they are on the left. So that means that the configuration on the left will have a greater moment of inertia about the axis indicated than the arrangement on the right. Here, the balls are all the same distance from the axis on the left and on the right, but the balls on the right are bigger. They have more mass. More mass is going to give us a greater moment of inertia, so this time the structure on the right has the greater moment of inertia. And here we have two identical structures, but on the left, we're rotating it about its center, and on the right, we're rotating around an axis which is displaced from the center. And it turns out, when you displace the axis, it changes the moment of inertia. And it turns out that the smallest moment of inertia in a given direction is the one you get for an axis which goes through the center of mass. So that means the left configuration will have a smaller moment of inertia than the one on the right. Okay, now how do you actually calculate the moment of inertia? The moment of inertia, if I have a bunch of point masses, I can find the moment of inertia by taking each point mass times the perpendicular distance from the axis squared, and then I just sum that for all of the points, all of the point masses. So for example, this shape right here, if I wanted to calculate its moment of inertia about the red line, about the axis that is shown, well, it's just, well, each of those balls, I have 8 balls, but they are all the same distance from the axis. So the moment of inertia is just 8 times the moment of inertia of one ball. And the moment of inertia of one ball is just the mass of one ball times the distance of that ball from the axis. Well, to find the distance, there's a displacement at x and a displacement of y in y. Each of them, if I call the length of the rods L, each of those displacements is L over 2. And then I just use the Pythagorean theorem to find the magnitude of the displacement from the axis and then square that. And when I simplify that, it just turns out to be 4m L squared. So each mass contributes an amount 1/2 m L squared. Now, if I have a continuous distribution, instead of summing mass times radius squared, I integrate radius squared times dm, times a little bit of mass. So I break my object into an infinite number of infinitesimal masses, and I add together mass times r squared for each little infinitesimal piece. You can also think of this integral, you can think of the little pieces of mass as density times a little piece of volume. So for example, if I wanted to find the moment of inertia for a cylinder about its axis of symmetry, I have to perform this integral. So to do this integral, I need to break it up into little pieces of mass, and each of those, for each piece of mass, there should be a well-defined distance from the axis. So if I just slice this up like horizontally, along one slice, there would be pieces of mass that had different distances from the axis. So instead, I'm going to chop up my integral into little pieces that have the same distance from the axis, little cylindrical shells. And I'm going to label each of those shells with their distance from the center, from the axis. And then I'm going to integrate from r equals 0 out to the radius of the cylinder. So if we look at just one of these slices, the volume of that slice is just the height of the slice times the circumference, 2 pi r, times the thickness of the slice, which is dr. So if I plug that into my equation for the moment of inertia, I get an equation. The 2 and the pi and the rho and the h all come out because they're constants. All right, and then there's an r in my dv, and there's 2 more r's, there's an r squared in my equation here, so together I get r cubed. And then I integrate from 0 to the radius of the disk. And when I do that, all right, the integral of r cubed is 1/4 r to the 4th, and I evaluate that from 0 to r, and I get this. So that is the moment of inertia for my disk, right there. Well, instead of writing this in terms of height and density and everything, we can also write this in terms of the mass of the disk. The mass of the disk is just the density times the total volume of the disk. And the total volume of the disk is the height, or of the cylinder, is the height times the surface area, pi r squared. And so I can then use that to rewrite the moment of inertia for a cylinder about its axis, and it turns out it's equal to 1/2 mr squared. And notice it doesn't depend on the height of the cylinder, the length of the cylinder, only the radius, because the radius affects how the mass is distributed away from the axis. If I had a lower density cylinder with the same radius and a bigger length such that it had the same mass, it would have the same moment of inertia, because moving mass along the direction of the axis does not change the moment of inertia. But if I had one with a greater radius but the same mass, that would have a different moment of inertia, because that changes the distribution of mass relative to the axis. Now, if I wanted to find the moment of inertia for a cylinder about a line which is perpendicular to the axis of symmetry, that is not equal to what we found. What we found was specifically the moment of inertia for a line through the axis of symmetry. So if we wanted to know what the moment of inertia was for spinning a cylinder along the axis shown in the picture, we'd have to do a different integral. And if you did it, it would turn out to be equal to this. And notice this time it does depend on the height, because if I have a taller cylinder, that's distributing more mass further away from the axis, and so that will change the moment of inertia. What about the moment of inertia about this axis right here? What is that equal to? It turns out that it's different than the moment of inertia about the axis, about an axis going through the axis of symmetry of our cylinder. By keeping the direction of the axis the same, but moving it to the side, we've changed the moment of inertia. So even though we didn't change the direction of the rotation axis, by moving the position, we changed the moment of inertia. How can we find the moment of inertia of the cylinder now? Well, we could slice up the cylinder in pieces with a constant radius away from the axis, but as you might guess, that's looking like a harder integral than what we did before. But there's a trick we can use, so we don't have to do that integral. And that trick is known as the parallel axis theorem. So the parallel axis theorem allows us to find the moment of inertia through one axis from the moment of inertia about another axis which is parallel to the first one. And just to show where this comes from, let's start with our equation that we integrate to get the moment of inertia. It's just the integral of the perpendicular distance from the axis dm. All right? But now we can write that perpendicular distance. Let's assume that the axis is in the z direction. Therefore, the perpendicular distance of any piece of mass is just x squared plus y squared. So the perpendicular distance squared is x squared plus y squared, right? And the z position of our mass doesn't matter, because that's along the direction of our axis, because I've explicitly said we're assuming that the axis of rotation is in the z direction. Well, now imagine that I offset the axis. So it's still in the z direction, but I've moved it. What is the moment of inertia now? Well, it's the same integral, only now I'm going to offset my integral by a vector which has an x component of x naught and a y component of y naught and no z component. All right? So I'm just transformed, and I'm doing this integral about a different axis now. Well, I'm going to multiply out these squareds, and this is what we get, right? X squared minus 2x x naught plus x naught squared, and over here we get y squared minus 2y y naught plus y naught squared. All right? And now I've got this big sum in my integral. I'm going to break it up into three different integrals. In the first integral, I'm going to keep the x squared and the y squared. In the next one, I'm going to keep the x naught squared and the y naught squared. And then the rest of the stuff goes into this integral here. Well, notice this first integral. What's that equal to? Well, that's just the moment of inertia about the original axis before we offsetted it. It's just before we offset the axis. It's just I, our original I. What is the second integral? Well, x naught and y naught are constants. So x naught squared plus y naught squared comes out of the integral, and then I just have the integral of dm. If I just add up all the little masses, I'm just going to get the total mass. So I can rewrite this thing right here as the first integral was just the moment of inertia about the original axis. The second term is just x naught squared plus y naught squared times the total mass. And then we have this other integral right here. Well, first of all, notice that x naught squared plus y naught squared, that's just the distance we displaced the axis by. So that's the distance, the perpendicular distance between the original axis and the new axis we want to find the inertia around. So we can write this term as just mass times that perpendicular distance squared. And notice this right here, x naught plus y naught, that's what we would get if we just took the position of each mass and dotted it with that perpendicular distance, x naught in the I hat direction plus y naught in the y hat direction, right? Now, if r has a z component, it doesn't matter because r perpendicular does not have a z component. So when we do the dot product, all the z components, the z component of r is multiplied by 0 and it goes away. So basically we have this integral right here. Well, the distance we displace the axis is a constant, so that can come out of the integral. And so now I have -2 r perpendicular dotted with this right here. But the integral of r dm, as you recall, is just the center of mass. So if we divided that by the total mass, it would just be the center of mass. So I can rewrite that integral right there as r center of mass, times, I forgot, times the total mass. There we go. So the moment of inertia about an axis that is offset, that's in the same direction as our original axis, but offset by an amount r perpendicular, is just the moment of inertia about the original axis plus m times r perpendicular squared minus this thing right here. Well, what is this thing equal to? Well, if our original axis was about the center of mass, then our center of mass is 0, and this term goes away. In other words, I offset is just I about the center of mass plus m r perpendicular squared. So if I know the moment of inertia for an axis that goes through the center of mass, I can find the moment of inertia for any other axis which is parallel to that simply by taking the moment of inertia about the center of mass and then adding m r perpendicular squared, where r perpendicular is how far we moved our axis from the axis that goes through the center of mass. Now, you can also solve this for I center of mass. If I know the moment of inertia about some point, and I know how far that point is away from the center of mass, I can just move m r perpendicular squared. I can subtract from both sides to move it to this side of the equation, and now I have an equation that will tell me the moment of inertia about the center of mass. Well, imagine I knew the moment of inertia about some axis A, and I wanted to find the moment of inertia about a parallel axis B. So this is only good for parallel axes, right? If I, know the moment of inertia about the y-axis, I can't use this to find the moment of inertia about the x-axis. But if I know the moment of inertia about the y-axis, and I wanted to find the moment of inertia about some other axis in the y direction but displaced, for example, this would work. So again, let's imagine I know the moment of inertia about some axis A, and I want to know the moment of inertia about some other parallel axis B. Well, what I can do is I can take the moment of inertia about axis A, and I subtract mass times the perpendicular distance from A to the center of mass squared. That will give me the moment of inertia about the center of mass. And then I can find the moment of inertia about B, because the moment of inertia about B is just the moment of inertia for a parallel axis going through the center of mass plus mr, and then the distance from the center of mass to B squared. Okay? Now, with that in mind, we can now find the moment of inertia for our cylinder, but rotating not about its center, but about its edge. So the moment of inertia is just the moment of inertia about the center of mass, about the center of the cylinder, which is, we found earlier, 1/2 mr squared. Then we just have to add m times how far we displace the axis squared. And the distance in this case that we've displaced the axis is r, 1 radius, so that's just mr squared. Add them together, and therefore the moment of inertia for a cylinder spinning about its edge, about an axis which is parallel to the symmetry axis of the cylinder, but about the edge of the cylinder, is just 3/2 mr squared. So let's do an example. Let's estimate the moment of inertia for SpaceX's Falcon Heavy rocket. And to do that, we're going to approximate the Falcon Heavy rocket as a cylinder with a diameter of 3.7 meters, a height of 70 meters, and a mass of 5.49 times 10 to the 5th kilograms, with 2 cylinders attached to its side, which are also 3.7 meters in diameter, 48 meters tall, and each with a mass of 4.36 times 10 to the 5th kilograms. So what is the moment of inertia of the rocket about the axis shown in the figure on the left? Well, we're given the mass of each cylinder, and we're given the diameter. If we divide that by 2, we get the radius of each cylinder. The heights of the cylinders don't matter, right? Because the height is a displacement along the direction of the axis. So all we really need to know is the mass and the radius of each. And then we just add the moment of inertia for each of them. So we're going to have the total moment of inertia is the moment of inertia for the central cylinder to rotate about that axis, plus the 2 boosters. But each of the boosters is the same distance from the axis. There's some symmetry here. So each of the boosters should have the same moment of inertia. So we'll just do 2 times the moment of inertia for one booster. The moment of inertia for the central cylinder is just the moment of inertia for a cylinder through its axis of symmetry. We already calculated that. That's 1/2 mr squared. For the boosters, however, the boosters are offset from the symmetry axis. So the axis that we're rotating about is offset from the axis that goes through their center of mass. So we're going to use the parallel axis theorem, and we're going to say the moment of inertia for a booster is the moment of inertia through the axis that goes through its symmetry axis. But then to offset the axis, we have to multiply by m times how far we offset, and the distance we offset is 2 radii squared. And remember, the center cylinder and the side cylinders have the same radius, so we don't have to indicate which one, it's just r. All right, and then if you simplify that, 2 squared is 4. To get a common denominator, we multiply by 2, and we get like 8/2 plus 1/2 is 9/2 mass of the booster times r squared. So that means that the total moment of inertia for this entire system is 1/2 mass of the center cylinder, r squared, plus 9 times the mass of the boosters times r squared. Factor of 9 is pretty good, pretty big, right? That having that extra stuff on the sides adds a lot, because moment of inertia, right, for a mass, for a point mass, goes as mass times radius squared. So as you increase that radius, it grows quite a bit. And that is our presentation for today. We'll see you next time.